Okay, I'd like to go back to the same example we did for displacement and distance and redo it for velocity and speed. So we have this clock. Remember, it's 30 centimeters in diameter, we said. And the second hand starts at the 12. And first it goes all the way around over the course of 1 minute. And we want to know what's the average velocity for that process, what's the average speed for that process, and is the velocity constant, is the speed constant? Okay, so first of all, let's do for 1 minute. Let's do first, is the quantity constant or is it not constant? Okay. The speed in this is going to be constant because the rate at which the second hand travels around does not change as the hand is going around the clock. It goes around at a steady rate, and the rate at which the second hand goes around the clock doesn't change. It always goes around at 1 second per second, so to speak. But the velocity is not constant. It's constant in magnitude, but not direction. Okay, let me explain. Consider the tip of the second hand here at several different moments as it goes around. So like maybe it's here, and then it's here, and then it's here, and then it's here, and then it's here as it goes around. I'll just do the 30-second case here because that'll be enough to sort of consider both at once. Which way is the velocity? So obviously it's going around clockwise. So up here, the velocity is going to point this way. Here, the velocity is going to point down and right. Here it's down. Here it's down and left. And here it's going to be left. So the direction of the velocity vector is going to loop around just as the second hand is looping around the clock. So the direction of the object's velocity vector is constantly changing, but the magnitude of the velocity remains the same throughout this entire process. And that's true for the 60-second and the 30-second case. So this is actually true, also true for 30-second case. All right, now what about the calculation side of things? The average velocity versus the average speed. The average velocity vector, remember, is calculated as the displacement over time and remember, the displacement of the second hand is 0 in this case. So as a result, average velocity is also 0. That might sound weird, but you know, it shouldn't, because that's just how these quantities are defined. The average velocity does not depend on the actual path taken by the object. It only depends on where it starts and where it ends. Since the object started and ended in the same spot at the 12, it had 0 displacement, so as a result, the average velocity was 0 because it didn't go anywhere. On the other hand, the average speed over 1 minute is not 0 because this one is going to be distance over time. The distance traveled was the circumference of the circle. So that was, let's see, if memory serves, I think it was 0.94 if you look back at the other video. And the time is going to be 60 seconds. So that's going to give me an average speed of around 0.016 meters per second. So there's the average speed. Notice, by the way, the average speed is positive. It totally doesn't matter which direction the object moved in. There's no possibility that this could be anything but positive. And also it doesn't have any direction associated with it. It's just a number. Okay, so there's the average velocity and average speed. What about over 30 seconds? Let me see if I can squeeze this into the bottom. What about over the course of 30 seconds? In this case, the average velocity is going to have a magnitude and a direction. The magnitude, by the way, the magnitude of a vector, I don't think I mentioned this in the earlier videos, but the magnitude of a vector can be denoted by putting it in absolute value signs. So the magnitude of the average velocity vector is going to be the displacement over time. So over 30 seconds, the displacement is going to be the 30 centimeters or 0.3 meters over 60 seconds. So that's going to be 0.005 meters per second. Okay, significantly lower than the average speed, as you would expect. And then the direction of the average velocity is going to be minus y direction, downwards. Because the direction of the average velocity is going to be the same as the direction of the displacement vector, which, as we talked about previously, it goes from the beginning to the end. So the displacement vector points downward, and therefore the average velocity also points downward. For the average speed over 30 seconds, it's actually going to be the same as this, the same as it is over 1 minute. If you want to recalculate it, you can. You would end up doing 0.94 divided by 2 is the distance traveled, divided by 60 over 2, because it goes half the distance in half the time. But of course, that's not going to make any difference mathematically, and you're going to get the same final answer. So the average speed, remember actually at the beginning here, we said that the speed was constant, and that's why the average speed doesn't matter whether you consider 30 seconds or 60 seconds, because it's always the same, but not true for the average velocity. So that gives you some flavor for how average velocity and average speed actually mean quite different things. And also don't forget that the instantaneous velocity is not the same as the average velocity. The instantaneous velocity is what I drew in this picture here, where the direction is always tangent to the path. How to calculate the magnitude would be a little bit more complicated, but you can at least see what the direction of the instantaneous velocity is. It's always changing and it's always tangent to the path.